Today we're talking about theoretical and experimental probability. So let's talk about what they mean, theoretical and experimental probability. Let's look at an example to start with. If I was to ask you what's the probability of getting tails when I flip this coin, what would you say? If you say 1/2, you would be correct. And the reason is that there are two possible outcomes, heads or tails. And if I'm going to flip it once, I would think that half the time I would get tails. So that's called theoretical probability. And here's the notation. We put a capital P and in parentheses whatever thing we're looking for. Now let's talk about experimental probability. Experimental probability is what actually happens. So here we're thinking what should happen by saying 1/2, but experimental probability would show us what actually happens. So I'm going to flip this coin 6 times and see all of our outcomes and see if we actually end up with tails half the time. So on our first coin toss, we get tails. On our second coin toss, we get heads, and that's kind of what we think is going to happen, right? On our third coin toss, we get tails, again, what we would think would happen. On our fourth coin toss, we're going to get heads. Interesting. It's coming out exactly like we think it would. Fifth, we get tails. And sixth, we get tails again. It's actually highly unlikely you're going to get exactly 1/2, although that could happen. So the probability of getting tails in real life ended up being 1, 2, 3, 4 out of 6 outcomes. And if we simplify that, that would be 2/3. So our experimental probability of flipping a coin and getting tails is 2/3, and our theoretical probability of flipping a coin and getting tails is 1/2. So we have a formula for these ideas. First, we have theoretical probability, which is what we think should happen. And the formula is just written out in words here, but you already understand it. It's the number of times the event should occur over the total number of possible outcomes. So we thought that the tails should happen once out of every 2 times we flip the coin. And then experimental probability is what actually happens. And the formula there is the number of times the event does occur over the total number of possible outcomes. So we saw that every 4 out of 6 times we actually ended up with tails in that example. So let's say we're looking at a 6-sided die. So this has the numbers 1 through 6, 1 on each side. What would be the probability of rolling a 3? And we're thinking theoretically here. 1 out of 6, right? Because one side has a 3 out of 6 sides. So based on that, let's work with some more theoretical probability. Find the probability of rolling a number divisible by 2. Now you may be able to do this very quickly in your head, but when you get problems that can be challenging, the easiest thing to do is to list all your possible outcomes and then list that over the total number. Find the outcomes of what you want and list it over the total number of possible outcomes. So let's list all our outcomes. We have a 1, a 2, a 3, a 4, a 5, and a 6. Out of these, we want all the numbers that are divisible by 2. So that would include 2 itself, 4, and 6, all our even numbers. So that gives us 3 possibilities out of 6 that would be divisible by 2. So that would be a probability of 1/2. So what if I asked you to find the probability of rolling a prime? Again, if you list all of your possibilities and then check off what you're looking for, that can be very helpful. So primes, 1 is not prime, 2 is prime, 3 is prime, 4 is composite, 5 is prime, 6 is composite. So this actually ends up being 3 out of 6 or 1/2 as well. When you think about probabilities, all probabilities are going to be between 0 and 1 inclusive. In other words, the probability of something happening at least is 0. There's no chance it can happen. Where if it absolutely is going to happen, it would be 100% chance, and 100% is the same thing as 1. So let's look at some examples. Find the probability that it will snow on an 80-degree day. 0, right? And what's the probability it will be cold on a 0-degree day? It's a 100% chance, so we would write that as 1. It's going to be cold on a 0-degree day. Another thing to keep in mind is that the more times you conduct an experiment, the closer the experimental probability will be to the theoretical probability. So for example, if we go back to looking at the coin toss, the more you flip that coin, the closer your experimental probability will come to equaling 1/2. Now in this example it actually equaled 1/2 until we moved on to the sixth trial. Really the sixth trial is where it changed. Typically, however, the more you conduct the experiment, the closer the probability will get to what you expect. So for example, if we were working with the die that has 6 sides, we know that the probability of getting a 3 is 1/6. The more we roll the die, the closer that probability is going to hover around 1/6. So this is why probability, theoretical probability, is used in different applications in the real world. So for example, it is used in calculating risk for companies to ensure their employees or themselves. So all the calculations are based on theoretical probability of risk, not on what's actually happened. So let's talk about some definitions. First, the first definition is outcomes, or the results. The next definition is sample space. This is a set of all possible outcomes. So when I suggested that you list all the possible outcomes with your die, and we listed 1, 2, 3, 4, 5, 6, this is referred to as a sample space, or list of all possible outcomes. An event is the specific outcome you were looking for, a subset of the sample space. So for example, if we're looking for getting an even, we want to get an even number. Another example, rolling a 2 or a 3 when you roll a die. An outcome would be, for example, 6 if that's what you rolled. And then the sample space is the list of all the possible outcomes, and the event was trying to get a 2 or 3. The probability of an event, whatever the event is, trying to get a 2 or 3 in this example, is the number of outcomes favoring that event divided by the total number of possible outcomes, where E equals the event. Now we've already described this. Again, the probability of getting a 2 or 3 in this case, well, how many, 2 or 3 means either one. 2 and 3 would be impossible, right? We can't get both a 2 and a 3. So how many sides altogether have a 2 or a 3? 2, right? Out of how many total sides? And we can see them right here in our sample space. 6. So again, we're just using this formula, which is another way to write the formula we saw for theoretical probability. Here's an example of a sample space where we have 2 dice, and we're looking at the sums of what the 2 dice give us. So on this example, that the red die gave us a 1, and the blue die gave us a 1, and their sum is going to equal 2. So we rolled a 1 and a 1 and ended up with a sum of 2. So our sample space are all the sums. So we're asked, if two six-sided dice are rolled, find the following probabilities. The probability of a sum of 6. So we can come into our sample space and highlight all the sums of 6 right here. So there's 5, so that would give us 5 out of, well, how many outcomes are possible? How many total outcomes are possible if you roll 2 dice? Well, we have 6 outcomes for one and 6 for the other. If you multiply that together, what do you get? 36. So the probability of getting a sum of 6 is 5 out of 36. The probability of an odd sum, we can come in here and highlight our odd sums. We have 3 is odd, 5 is odd, 7 is odd, 9 is odd, and 11 is odd. And if we count those up, you've probably already figured out that that's 1/2, right? Or 18 out of 36. A composite sum, what's composite? If you said the opposite of a prime, you are correct. So it's anything that's not prime. So we're finding a sum that is composite. Well, 2 is prime, 3 is prime, 4 is composite, 5 is prime, 6 is composite, 7 is prime, 8 is composite, 9 is composite because 3 times 3 equals 9, 10 is composite, and 12 is composite. So if we count all these up, we end up with 21 out of 36, and we can simplify that because 3 goes into 21 7 times and into 36 12 times. So let's look at another example. In this example, find the probability of getting a 2 if you spin the spinner. Probability of getting a blue if you spin the spinner. 2, right? I accidentally said that. So 2 out of how many possibilities? 4, which gives us 1/2. What is the probability of landing on a red if we spin the spinner? 1 out of 4. What's the probability of landing on a 3? Also 1 out of 4. So what's the probability of landing on an even or a blue? So or means include both. So even, but we also don't want to count anything twice. So for even we have a 2 and a 4. And for blue, we have a 3 and a 1. So it's actually all of them. So how would you write all as a 1, right? It's a 100% chance, so that's 1. What about green or odd? Green and odd. So green and odd means that the number has to be both green and odd. Well, our only green one is even, so the probability is what? 0. That can't happen. We can't land on one that's both green and odd. What about the probability of prime or blue? So let's see, we have for prime, we have the numbers 1. I'm sorry, 1 is not prime, is it? Good catch, whoever realized that. 2 is prime and 3 is prime. And then for blue, we have 3 is blue and 1 is blue. So if we draw a Venn diagram over here, for blue we could have 1 and 3, and for prime we could have 3 and 2. And so they intersect at 3. We don't want to count that 3 twice. We only want to count it once. Where they intersect, we only want to count once. So there's only 3 out of 4 in this example. So our probability of prime or blue is 3/4.